physics, um, atoms, quantum mechanics. Delicious.
Delicious?
Delicious. Oh, I had chicken shawarma. So good. So good. I don't have it every day. I maybe have it once every week or two. Maybe once every 2 weeks at the moment because it's so hot. Right. Oh. Was the image there a minute ago of my laptop? No?
No, it's a second.
Maybe. Yeah, but I'm not doing something stupid like it's not plugged in. Oh, it is plugged in. It's not that slow. Is that? Hang on, let me just. Did this happen last time? And what did I do last time? Oh, oh that's not going to be a good solution.
Let's go to the B. So,
No, I can't. That's where I was. Now that's good. That's good. So it means whatever cable this uses, I can just take the. Okay, so this. I take this one out here and put it in here.
genius.
Not really.
That's it. Oh, yeah.
Ah, wonderful. Wonderful. Last topic. Quantum mechanics. What you've all been looking forward to. Sorry. No, I just knocked it out. Relax. There you go. Thank you, Wookie, for fixing the screen. I was talking to Dennis, and good news, he gave me permission to sit in on the presentations.
It's a waste presentation.
Waves, Wookies, and Rawans. And Bruce?
And
what are you doing, Bruce? Huh? Oh yeah, Bruce, I'll listen to your one too. No, not everyone's session, just those people.
yeah, in everyone's session. Because you're in different groups.
No, I have the times. He gave me the times for everybody's presentation. My physics is a bit, so I want to learn some more physics.
I'm not talking about relativity, I'm not talking about
Huh?
Maybe a question.
Oh, no, don't worry. No, don't worry. It'll be good. I promise-ish. Okay, quantum mechanics then. I guess I'll find out tomorrow.
I will talk about it.
Ah, don't worry. I'm not going to do anything weird. You don't have to worry.
Don't tell them like, oh, you should have talked about it.
Do you think afterwards I'm going to turn to Dennis and go, well, that was terrible. Let me tell you everything that was wrong with that. I'm not going to do this. I'm only going to say positive things, I promise you. No, I will. Trust me. I think it's great that you're doing this, and I will only be there to support and to learn something. You're confident I'm not going to learn anything from your presentation? Not even one little piece of information? Are you sure?
Yes.
You might It's very nice of you to say that. This is Connell. Oh, who's this? Do I want to answer?
Speak it out.
No, it's not the principal. Oh no, it might be. Hello?
Hello?
It is.
What does it mean it is?
It is.
Yeah.
Is it season? It is.
Oh yeah. Hello. What's the response? Like,
This is Wookie.
this is okay? It is. Is it right? It's common conversation. In the phone.
Nothing, we say all wrong now.
Right. In Korea?
Upsell?
Upsell, yeah.
Is it Korean? I didn't know the
Yeah.
That's
it.
No, this not.
Everyone is good.
Yes? No,
His English is very good.
he's an actor. Apparently he's not a singer.
He is singer.
But he's an actor. See, I thought acting.
No, you go and do your documentation.
No.
He was in the USA.
What is he doing? He is an actor. What the hell? He's an American?
Not actor. Not actor, singer. Because you know there are.
There's a guy who looks like him.
Yeah.
Are they brothers?
Not. The similar guy.
The guy from Suits. Yeah, Park
It's different guy.
But they look the same.
Absolutely different.
Is this guy famous?
You know, he's singer and actor.
Also,
I'm Barry.
but he looks like Eric now.
No, absolutely not. Where's Barry? This guy is just like singer. You know Super Junior. Singer.
Yeah, that's how I know.
Actor and singer. The main job is singer.
He went to National Service.
National
Service.
National Service. Ah, yeah. Yeah, he's doing now? I don't know.
Hey, if he's Super Junior. They are old.
Yeah, not
Super
junior.
Junior. They're like old. What's the new one? Yeah. Yeah, very.
Nothing.
He is famous.
Where? Malaysia.
He's hot.
He's hot?
Yeah.
No.
The girl from Oh My God, that's small.
That girl?
Yeah.
Like
Chao Bu.
volleyball, like volleyball.
No, that is Chao Bu. That girl is warm. No, what? No, that's Chao Bu.
Alright, let's start. Quantum mechanics. Yeah, it looks like a lot, but it's actually not so bad. So anyways, you've seen this equation before. Whose equation is this?
Newton.
Very good. And it's for gravity, and you know that such an equation would cause this type of motion, circular motion.
Yeah.
Or what's the other type of motion? Elliptical. And who first said that? Kepler, yes. Now, you notice how the situation is quite similar.
Coulomb.
Can you see how they're similar pictures?
Yeah.
The formula, similar. And the picture looks similar as well. So you would think that everything should be the same. But it's not quite. So remember when I told you that distance is not discrete, that you can have any distance you want, any 10 to the minus 15, 10 to the minus 16, all this type of stuff. I lied when I said that. It's not true.
You lied.
I lied, yeah. And that's my reference. You can't actually have any distance you like. So what was discovered here with this picture is that the electron could be here, maybe it could be here, but it can't be in between. Now you kind of know that already from chemistry because you have orbitals. And there are only certain orbits that the electron will take.
Bohr.
Huh?
Suggested that.
Bohr suggested it, correct, yes. Bohr is quantization, yes. Now, this is the picture you have from chemistry. But, I mean, this is not new information. You should all know this. It's basic chemistry, that the electron can sit in only certain orbits. But this is quite strange from physics point of view, because in physics, the formula is the same. However, when we look at the Earth and the Moon, we don't say the Moon can only be in certain orbits. It can be in any orbit. Although when we look at this picture, we now have to say the electron can only be in certain orbits. So this is quite strange. But you know this from chemistry, yes? No what? Oh, fine. Now, we need to... I don't think you need to draw this picture because you have this picture from chemistry, right? In fact, not only do you have this picture, you also have the names of the orbits as well. But what you might have to draw is this. I'll have to explain how this picture is made. Let's start firstly with this. Here it says black body. What that means is it's a pure white light source. Pure white light. And you put this white light through a prism and you get the colours of the rainbow. Now you all know this from middle school, I think. It was Newton who did this with the prism, wasn't it? He put the light through the prism and he saw the rainbow colours. Yeah. Now this picture here is a little bit different. What you have here is a hot gas. And this hot gas is glowing and it's releasing light. So, you know, like a fireball, you know, it's glowing orange or whatever like this. And this picture here is a little bit different again. This is pure white light and you shine it through a cold gas. And what I mean by a cold gas is one that's not glowing. It's like maybe at room temperature or something. You know, like say nitrogen or helium or whatever. And you get three different pictures. So we need to explain what each picture is and why we got it. So the first one is just all the different wavelengths of light. All the different frequencies, all the different colours and energy of light. Okay. Now why do we get this picture here? We'll get to that one in a minute. It's a little bit easier maybe to look at this one first. So, what's happened here is each of the atoms have electrons, and the electrons are in different orbits. What's the first orbit?
1. K.
1s, is it?
Yeah.
Yeah, and the next one?
2s.
2s. Why, are they two different orbits, or they're two different...
Two different.
They're the same radius, aren't they? 1s, 2s.
Different.
1 and 2 is different.
Different radius.
Yeah.
Oh, okay, right. So 1s and 2s then. So, here's the upper orbit, here's the lower orbit. Which one has more energy? The upper or the lower?
Upper.
Which one has more energy?
Upper.
Oh no, the upper one, yes, it has more energy, doesn't it? So if you want to go from here to here, you need to have enough energy. Because remember, we said we can't go halfway, because we can only go in certain orbits. Yes, we can't go halfway. So, if a photon comes in and hits the electron, if it has enough energy, it will jump up. But if not, nothing will happen. Okay? So, the reason you have these black lines here, it represents the right level of energy for one of the electrons in one of the orbits to take it and jump up in orbit. Okay, so this one here, what must have happened was there's some electron that wanted this amount of energy, took it and jumped up in orbit. And so we don't get this light, because this light is missing because it was stolen from the electron to jump up in orbit. Okay, so it was the right amount of energy to free the electron from its orbit and move it up to another orbit, or maybe to move it out of the atom to ionize it. In other words, it was able to take this energy. Yeah?
You mean if electron is jump up, that means that is the black.
Yeah.
If open,
What do you mean?
if electron jump up, we can see that
Oh, sorry, I'm sorry, I said that backwards,
Different.
did I? No, that's right. Here and here,
yeah.
this one has more energy, this has less energy.
Yeah.
They're both negatives.
Yeah.
So if this one wants to move up, or even if this one wants to be freed, it needs to get energy.
Yeah.
So the photon comes in and takes the energy from the photon. So the photon is now gone.
Yeah.
So that photon with that frequency is gone. So that's why we don't have the colour. Because the light went in to the cold gas, some of the electrons took some of the photons, and so not all the colours came out, because some of the frequencies are missing. Do you understand? Some of you look confused. I don't know what's confusing.
Right.
Is it?
It's block, like block.
Like a block, yeah. Or I prefer stolen.
Yeah.
Yeah. Like imagine here, low orbit, higher orbit, higher orbit, higher orbit, okay? If a light comes in and hits him, if it has enough energy to jump from there to there, it will take the light photon and it will make the jump, okay? If it doesn't have enough energy, it won't take the light, because it can't jump halfway. So the photon just continues on its way. Yeah. If it had enough energy to jump from there to there, it will take that and it will jump. Or if you had enough energy to jump there to there, it will take it and it will go. Or if you had enough energy to be freed, you will take that. So all these black lines represent energies that some of the electrons took to be freed. No? Oh, what's confusing here? Tell me. You look so unhappy. Is it the heat? It's too hot, isn't it? Go on, yeah, what are you asking me? Okay, you don't know what to ask me. Anybody else?
But why there is gas?
It's very difficult to shine light through solid objects. Gas is easier.
Yes. Right.
Yep. You know, like which would be easier to shine light through, a gas of oxygen or a piece of wood? Yeah. That's the only reason it's gas. It doesn't have to be a gas. It's just practical. Yeah. Yeah? Is it okay? You don't look like it, especially you, Wei. Is it okay? It's okay? Alright. That's called the absorption, because what does the word absorb mean?
H.
Just like that, yes, okay. This one's called the emission spectrum.
Release.
Release
energy.
Yeah, releases this, yeah. Whereas this one, it passes through.
Yeah.
Okay, so then think about what happens here. So you have a hot gas, so you heat the gas. So what happens to the energy of the particles as you heat the gas up?
Energy goes.
It increases, doesn't it? Yeah? So you have this energy and it's all moving around, so things are moving quite fast. Now, suppose we said this one has higher and this one has lower. Suppose an electron falls from the top to the bottom. Does it gain or does it lose energy? Loses energy, doesn't it? Now, that energy didn't just disappear. You can't just lose energy. You know, it has to be converted into something else. So in fact, believe it or not, when the electron, a bit like the photoelectric effect, you can go both directions. So, in the photoelectric effect, you said a photon could free an electron, but likewise the electron could become trapped and free a photon. Same thing happens here. If the electron is up here and it falls down to a state down here, then what happens is the photon is released because the energy has to stay conserved. So this electron moves down, it loses energy, but the energy can't be lost. So the photon is how the energy is converted, as released. Okay.
If you heat it, then it will lose energy.
If you
heat it, why would you lose energy?
I suppose, yeah. If
Please.
when you heat it, you're vibrating the molecule. I guess what you're trying to do is you're vibrating the molecule. That energy doesn't change; it just keeps vibrating. I guess you're trying to knock one of the electrons down a level.
Then when you cool it, the energy increases.
Here,
Yeah.
when you do what?
When you pass it through a cool gas,
Yeah.
you see they absorb energy.
Yeah.
Why? It's just like if it's cool, then it releases energy, and when it's hot, it absorbs energy.
I understand what's confusing here because we're using cool and hot to refer to the vibrations of the nucleus, not the energy level of the electrons. There's like two separate pictures in my head. Huh? Okay. Well, I'm referring to cool and hot. That's referring to the vibrations of the molecules, not the energy level the electron is in. So, for me to say that's hot, it just means everything is vibrating. And then I zoom in and look at just one atom. And I don't care that the atom's vibrating, I'm just looking at what the electrons are doing. Yeah. Really, the only reason about hot and cold here, the only reason for hot and cold is, by cold I mean you can't see it, that's all. Like, you can't see the oxygen in here, can you? I certainly can't see the oxygen in here, can you? No, you can't. Can you see the nitrogen in this room? No, so we say this gas is cold, okay? But if you heat up the gas, you could see it glow. Yeah, for example, the sun. Yeah. And isn't that what they do for the neon lights? Isn't it? Don't they heat up some neon or something? I don't know. But anyway, if you heat up a gas, it will glow. So in this situation, the light is coming from the gas itself, and in this one here, it's being absorbed. Anyway, back to what I was trying to say. So if it's in this orbit and it falls down, it releases a photon. Okay. But it can't fall down half an orbit. It can only fall down this much or maybe this much. So only certain energy levels get released. Only certain light gets released. Okay? Now, you've seen this in chemistry. I wasn't planning on taking so long on this. You've seen this in chemistry in something I think called a spectrometer.
Yeah.
Oh, no, this isn't part of the show. You've done spectrometer, right?
Not much.
What's a spectrometer?
We did.
Mass spectrometer. How do they work? You take a substance, you heat it up into a gas, isn't it?
Yeah.
And you shine light through it?
Electron. Bang, bang.
Oh, you fire electrons at it?
And
And then you measure where it hits?
Yeah.
That's it. Yeah, not that spectrometer. There's another Flip's sake. Now, the principle. Kalina. You intentionally called me. Yes. How can I help? Yes. Yeah? They need some more. Yeah, I don't have. Okay, are you telling me this for in future, or they're looking for something? Okay, I do not have anything like this because I use their marking grid that they provided. Yeah. Yeah.
You think plastic is
What? Malaysia. That's
and it's like you before.
in class.
Yeah.
Make something neat.
I think so.
Yeah, thanks. That is okay. That's means more like more understanding.
They say that in drama too.
Watch movie.
Oh my god. Isn't that like a prayer or something?
Tomorrow is your presentation.
Tomorrow. Why is tomorrow?
Rowan, did you get the email from NUIG to apply the scholarship? Did you apply? Why?
Closer. You apply?
No, I don't want to work here.
You don't want to go?
It's not my first choice. It's my second. I do pushing
Did you get the project?
I don't need second.
I mean like a career, you also don't have, you don't even need it. Free as playing Maggie. But you didn't pay. I did talk to him about it.
Did you pay? What's your
Same. Same like Korea. Korean media.
Did you pay?
I didn't.
Why?
Why? Why?
Why didn't you pay?
It's easy.
500.
Yeah.
It's not quite expensive. It's enough to support your.
What money? North Korea, South
No,
Korea,
I love
Israel.
power. And then I'm so there.
Really?
What power?
Not there. Conference.
North Korea? What? South Korea. From South Korea?
Where is this country?
真的很 cute，真的很 cute。
What?
然后这两个白色中间打开了，很多。
Oh.
North Korea has a higher currency than South
But
Korea.
this is natural. Even though, yeah, this is natural.
It's fake.
Their currency have no,
No value?
yeah, no value.
对啊，这个是点，这个是我们这个什么来着？诶，以前我有一个 app，很好，它问的是，叫做编辑。我觉得这个 app 一模买了全部从那个，我买这边买到我那些 upgrade 的卡，upgrade 到我的卡。
Oh, you know Eric Nam? Install and cost me money from Eric Nam. Eric Nam.
After summer sale, we start with the original price.
反正它一个里面不是它一个里面1 week 2 hours 什么的。你上次我们就说那个，
其实我还没有把我考完了，人家。
对啊，马上就。
After 2 weeks，
反正
Yes.
反正
Ah, what?
很可爱耶。
You look so
你作为一个男的在男的。
这个拿了一个。
So kind of bored.
我用来，你可以选。
He do look like
还有filter 吗？
he looks different when he was performing.
你可以找filter because there is no
It's not here.
我两个。
What the world? Okay, see.
越来越呢。对我。
Hey, he looks so different. He looks so different. It's so cringy.
给我那个。
Why do you like this kind of video?
Like?
Like, why do you like this kind of
What
video?
kind?
你
Eye
看后面，
performance?
觉得我看因为看觉得不一样。萌啊，那个我Maybe you want to see Korean.
Isn't that like their real voice?
Leave a lot.
I still for it. Sure.
You can see this kind of this kind of program.
Korean have a lot of
看那个 program review.
This program is so famous in Korea and I like to.
You can see
a lot of
famous
famous
stars.
star in this program. This means the channel is live alone. It's just showing the person live alone in their house.
哦，那个钓鱼在鱼啊。
It's like a reality show. It's like a reality show. It's like the camera follow them everywhere. It's like their real.
Yeah.
Yeah, nice. Is it singer or singer and actor?
Everything sounds like player. Model, announcer, singer, actor.
没有
Was not here.
我这里直接不错，还没动。
Where's here?
100啊。
I can't remember. The park guy. He looked like the Eric Namdak, yeah?
You have Korean drama? Korean keyboard. What is it? From Korea. You don't have Korean. No, because your phone is so slow.
Sorry, more flipping problems. Just a problem with the September results, that's all.
Was good?
No, they want more documents from me. Always something. Yeah. Anyway, as I was saying, no, please.
Where is your pen? Why are you?
Wookie.
Off the fuck.
Wookie.
Yeah, I'm here.
So as I was saying, in chemistry you have this thing called a spectrometer. I know you do mass spectrometer. So what they do is they take a material, they heat it up into a gas, and they shine a light through it, and they produce this absorption spectrum. Now the reason they do that is, believe it or not, each absorption spectrum is unique to each material.
Of course.
So it's like a fingerprint for the material. Every material will have a different absorption spectrum, which I think is quite interesting. So this is how they can identify what a substance is, by looking at its absorption spectrum. They can see, this is carbon and whatever, sugar or whatever, you know.
They heat the gas.
Oh, sorry, they heat it up enough to just make it a gas, but maybe not heat it up enough to glow. You know, because some things maybe have to get really hot to glow. Like, I don't know, how hot will you have to make this before it starts to glow? You know, maybe not as hot as I think, but it's easier just to turn it into a gas, you know, vaporization, and then just shine a light through it. And then they can use a computer to grab the absorption spectrum and compare it to a database to figure out what the material is. Okay, so I would like you to draw this down. This is important in physics and chemistry.
So actually the piece of line is not exactly one piece of line.
What?
Just second.
This one?
No, upper.
This one?
Yeah.
What?
The piece of color line
Yeah.
is not exactly one piece of color line.
I don't know, maybe it's 2. Maybe it's 10.
It's more.
Yeah, it could be.
Like zoom in, down.
Yeah, could be. That's not so much what I care about right now. I just need you to draw this, please. In this picture, make sure you have more black than you do have colours, and vice versa. Yeah. Oh, no, don't worry about that, yeah. Are we drawing over here? What's so funny? Just colour it in with your pen, that's all. Did you draw this? What? Why doesn't what?
Does not you don't have the black noise.
Oh, because the gas is hot, so it's emanating its own light. Can I continue? The slide has been on the screen way too long. Continuing. Now, so we've talked about this. If an electron falls from high to low, then it will release a photon. If an electron's in a low orbit and receives a photon with enough energy, then it will absorb the photon. Okay. Here's a simple example I want you to do. An electron falls from state 4 to state 3, and here are the energies it has. So in both cases they're negative. Why? Because they're trapped.
Yeah, trapped.
I want to know what is the energy of the released photon. Okay, should be very simple. What's the answer?
0.6.
0.66 electron volts. And how did you get that? Minus, because the photon's energy has to equal how much was lost. 0.66, yeah?
Yeah.
Right, very good. Now, here's one that is nearly the same. You have minus 13.6 electron volts, and then it received a photon, and that made it jump up to minus 1.51. Oh, sorry, that should say electron volts. So let me just draw that for you. So it's here in minus 13.6 electron volts, and it jumps up to minus 1.51 electron volts, and this is going to be because a photon came in and hit the electron, and the electron jumped up. So I hope you can do this. I want the frequency here. Now the idea is the energy that this photon has, it must equal the energy that the electron gains by moving up. Do you understand? Yeah? When this one moves up, it gains energy. Where did this energy come from? It came from the photon. Do you remember what the formula is for the energy of a photon? HF. And that should equal how much energy was gained. Now don't forget, we need to convert these into joules. Okay, I'll give you a minute to try that. I think this should be okay for you. Let me just open up my calculator too. So. Got it calculated? Yep. Yep. Okay. Oh, sorry, they probably don't have the numbers up there. So how much energy was gained firstly? Well, it went from minus 1.51 minus 13.6. So it gained 12.1 electron volts. Fair enough. What is that in joules? That's how many joules it gained. But where did this energy come from? It came from the light, and what's the energy of light? It's equal to HF. So HF is equal to this number. Yeah, so if HF is equal to this number, how can I get the F? Just divide by H. Yeah? So divide by, what number is H there? 6. This is the frequency of it must have been the frequency of the photon. Yeah? Okay. It's okay? Right. There's some nice little videos here if you want to look it up, but you did my active listening on quantum. Then you don't need to. Okay, so de Broglie noticed or considered something. So last time we said that a photon of light is like a wave, but also we can think of it as a particle. So de Broglie said, well, if we can think of electrons as particles, then maybe sometimes we can think of them as behaving like waves. Ah, look at that face. What an unhappy face. Let me explain. So, how can you tell the difference between a wave and a particle? It's very simple. You can use the double slit. Okay? If you have particles, when they come in and hit the double slit, some of them will crash here and some of them will crash here, because some of them went this way and some of them went this way. Fine. Now, if you have a wave that hits the wall, some of the wave will be here and some of it will be here, but also some of it will land here and some of it will land here. And we did this in waves. We actually even calculated, or we even have a formula for calculating the fringe separations here. Goodness, what was it? S equals lambda d over d, wasn't it?
Yeah.
Something like this. Anyways, that's how you can tell. So, if you use some light, you will get this picture. And if you use electrons, you'll get this picture. Right? Well, not always. So, with the electrons, it was quite surprising that the picture you got on the screen was actually this picture. So that means these electrons, they are waves. But you know they're not waves, because when you look at the atom, the electron goes in an orbit around the atom. And if it was a wave, then maybe it would be more like this. And it means the electron is everywhere. So you never see the positive proton because it's covered by a wave of negative electron charge, perhaps. So this is quite strange. And it gets a bit stranger, as you probably know. So this is what they decided to do. They said, right, is it a wave or is it a particle? I know what we'll do. We'll put a little detector here. We'll call it D1. We'll put a little detector here. We'll call it D2. And when the electron goes through the left one, this goes ding. And when it goes through the right one, this goes ding. And we can see we're trying to see what is happening. And then all of a sudden the picture returns to this. And then you turn the detector off and the picture goes back to this. It's like the electron knows it's being watched and changes its behavior at the slits. If you can see what the electron is doing, it will behave like a particle. If you cannot see what the electron is doing, then it behaves like a wave. How does the electron know it's being looked at?
Electrons have brain.
No.
Have sensor.
No. And you might say, okay, let's be sneaky. Let's try and trick the electron. So you might say, I really want to see what the electron is doing. So here, it comes along and it behaves like a wave. So you say, aha, I know what I'll do. I'll put the detector right at the end. So it doesn't have time to decide if it wants to be a particle or a wave when it gets to the slits. So it's coming along as a wave, it's coming along as a wave, you turn it on, and then all of a sudden, boom, back to particles. At the last moment, it can still change. It can say, oh yeah, I was a particle, all the way back here even. It's not only can it change its behavior, it can change its behavior in the past. Yeah, so it can appear to have been behaving like a particle all the time, even though it was behaving like a wave, up until you turned the detector on.
Maybe you know that thing that some people see as white and gold and some people see as blue and maybe something like that.
A bit more complicated than that, but it is kind of your perspective does change it. Yeah. Right, very strange. So de Broglie said, okay, particles can sometimes behave like waves. And if they behave like a wave, this is the formula for their wavelength. He said it will behave like a wavelength with h over p, where p is momentum. What's the formula for momentum? mv. Now, if you remember, in the last lesson I said it was important that h is small. This h is really, really small, which means the wavelength is really, really small. So this is why particles normally look like particles and not waves. Their wavelength is so small you can't actually see the wave behavior because it's such a small wavelength. It looks like it's moving in a straight line, but actually if you could zoom in on it, you can then see the wave behavior. So the h very small means the wave behavior only happens when you're very small, like an electron. It also happens with protons and neutrons, but because they're 1,000 times bigger, it means their waves are 1,000 times smaller and makes it even harder to see their wave behavior. But you can just about see the wave behavior with an electron. It's small enough that you can see the behavior. Okay? So this is de Broglie's famous formula for calculating the wavelength of an electron.
H is fixed number, but P
It's a constant, and P is momentum. So if you make the mass really, really small, like an electron, you make the wave behavior bigger. Also, if you make the V very, very small, you make the wave behavior bigger as well. So if you have a slow moving electron, it will display wave behavior.
H is
Not quite. No. The H over P is just the wavelength. The H doesn't really have any meaning like this. Not really. Happy? Why unhappy? It gets worse than this, but I won't bother. Okay. Continue. You got de Broglie's formula? So here's an example. An electron gun fires electrons at a speed of 0.1 c towards a screen which is 1 meter away. According to de Broglie, what's the wavelength of this electron? You've heard of electron gun in chemistry, haven't you?
Yeah.
What does an electron gun fire? Electrons, yes. So let's calculate it. So according to de Broglie, the formula is H over M V. What number is C, please? Is it? 28? Right, so de Broglie says the wavelength of this electron will be this tiny number. So if you want to see this wave behavior, you need to be able to see 10 to the minus 11 meters. Huh? Say again?
What's the P in for?
Momentum. Okay, can I do the next part?
Yeah.
So, these electrons are fired between a double slit of 10 to the minus 10 meters. What is the angle of the first order of diffraction? So, here's your electrons, and they spread out, and you have n equals 0 here, and this is n equals 1 and n equals minus 1. So, I want this angle. Now, you know the formula from waves. What is the formula, do you remember?
D sine theta equals n lambda.
Yes, I would say it backwards, so n lambda equals d sine theta. We want the theta, we know the d, we know the lambda, and we know the n. The n is 1. So the theta will be sine inverse lambda over d. Right? Yeah. Okay. Sine inverse lambda over d. 14 degrees is the first angle. Yeah? And finally, what is the fringe separation?
SD equals d lambda.
Yeah, what is it? S equals lambda d over d, isn't it? Now, in this question I said it's 1 meter, the distance between the gun and the screen.
Capital D.
Yeah, capital D. So, that's 1 meter. So it's just lambda over d. So if I just go back on the calculator, 24 centimeters. 24 centimeters is the fringe separation on the screen. So the electrons hit the screen 24 centimeters apart. Yeah. It's very strange behavior. Although it's a particle, it's like a wave is guiding it through space, and it'll move through space as if a wave was pushing it along. So it'll spread out, it will go here, it'll go there. It won't really go in a straight line. It's very strange. So we think of a particle just going in a straight line. But at this distance, at this small scale, it will behave as if it's, you know, on an ocean wave kind of spreading around like this. Very strange behavior. Okay, so continue. You got that? Yeah.
24 centimeters means the first angle between.
Actually, the distance between all of them is roughly 24 centimeters. The fringe separation. Yep. Okay. Right. Good news.
Finished?
Yeah. So, just the 2 questions here. Even though this was quantum mechanics, we only did one formula, de Broglie's formula. So, you know, it's literally page 1 of the Quantum Mechanics University book. So there's still 399 more pages of quantum mechanics, but page 1 is enough, trust me. Yeah. Right, I'll stop the video, and then if you can start these for a few minutes, please. And then next time we'll do tutorial and revision on Friday.